The keynote now about reinventing learning itself with digital technology will be delivered by Bror Saxberg. Bror Saxberg is Chief Learning Officer at Kaplan, and he has a strong mathematical and computational science background.
How do you actually use science and cognitive science to actually drive learning performance in practical ways? Kaplan is an interesting place to do this. Kaplan is a multinational education company. We have more than 1 million students a year from Singapore across the US into Europe, some in the Middle East. And we have a huge range of types of learning that we do, ranging from teenagers who we get ready to get into college through college entrance exams, to delivering associate's degrees, bachelor's degrees, master's degrees, even a doctoral program in nursing, a virtual law school. And then we also do corporate training as well. We're one of the largest providers of financial services training in the UK, the US, and Australia. And we have a very large English language learning group as well, 80,000 students a year doing a variety of things, either in universities or on their own to learn English. So when I was hired 6 or 7 years ago, the then new CEO had a team look around and realize we had reproduced inside Kaplan the chaos of the entire education sector. None of these folks could talk to each other. The university people could not talk to the test prep people couldn't talk to the corporate training people, nobody could talk to the English language learning training people, and it hadn't mattered because it was all accumulated. They all ran very happily on their own mythologies. I mean, why would I change? It's worked for decades to centuries to thousands of years, so what could I gain from this? So the CEO's point of view, because he had all of these that he was looking at, all of these, he said, why do we need so many user manuals for minds? We're not switching devices, it's a brain. So why aren't we benefiting from having 1 million students a year as opposed to it being all balkanized into different mythologies of learning? So, and then the key where they wound up hiring me, instead of picking one of the mythologies to be the critical mythology, they decided to ground what all the 100+ instructional designers do on learning science. So my title is Chief Learning Officer, but I'm actually Kaplan's Chief Learning Engineer, where a learning engineer is actually a missing category in our whole sector. If you think about a chemical engineer, for example, chemical engineers are not chemists. You would never hire a chemist to build a new pharmaceutical factory because you know the chemist doesn't understand economics or safety or health or any of that. And the chemists would agree, don't hire me for that. I don't want to do that. You hire chemical engineers who are people who love working on constrained design at-scale problems, applying chemistry to real-world issues. Well, now replace learning in there, right? We have a lot of very good people working at scale on learning, but very few of them ground what they're doing in the science of learning. There are very few learning engineers. I actually did an editorial for the Chronicle of Higher Education in the US on this and looked up. There are 30,000 working chemical engineers in the United States. When you round it, there are approximately 0,000 learning engineers working in the United States. Because the training isn't there and there's not a realization of this. So what I'm going to try to do in some ways is make you all learning engineers in about, 15 minutes. So let's see how we go. So the first thing is, there's a lot of good science to draw on. And the first part of it is, how do minds actually work? How does expertise actually work? And this has been validated in experiments all around the globe over decades. This is kind of, settled way of thinking about this among cognitive scientists. You start with audio and visual channels that feed what's called working memory. So working memory is your verbal memory. It's the part that you use, you have an internal monologue, you use it to solve your own little problems and the hardest things you do. It's very slow, but it's very flexible. And it is the thing that can confuse you and things like this along the way, but it is where you get to do new things. That is deeply supported by what's called long-term memory. So long-term memory is completely different. It is not verbal. It is non-conscious, in fact, but it feeds patterns, ideas, recognitions, even sophisticated processes into working memory so that working memory doesn't have to hassle with a bunch of complicated things that have been mastered in long-term memory. I know it's late in the afternoon. Let's try something. Who here drives a car? Raise your hand if you drive a car. Okay, that's good. I tried this in Singapore. It was a disaster. Okay. All right. Who here has had the following experience? You set out to drive to place A, and then you start thinking about life and family and the universe and the ELIG conference, and you look up, and you are at place B instead. Who's had that experience? Now, look around, look around. So you're not crazy, at least not for that reason, okay? This happens all the time, right? I'm so old, I just say I had the wrong program card in, and off we go. But we don't stop to think for a second. Who was in charge of a ton of metal moving at 30, 50, 100 kilometers per hour? I mean, you were not. You were manifestly thinking about something else. Some part of your mind took over and drove you to the wrong place. And this is not like breathing or digestion. I don't want to know what's going on there either. This is complicated. It's rules and people and speeding up and slowing down, right? So long-term memory, cognitive scientists find, is at the root of all expertise. All experts have a bunch of things, not everything, a bunch of things that are automated, that are so clear and so familiar that they literally no longer think about it. And as we'll talk about, that actually gets us into problems. So when you put all this kind of learning science together and then start to ask, what are the implications for actually designing learning environments? You come out potentially with something like this, which is how we think about it at Kaplan. You want to deeply understand expertise. What are the things that are in long-term memory? What are the decisions and tasks that experts decide and do? Then you want to be able to use evidence-based methods to attack those outcomes. If you want people to be able to decide and do things in certain ways, what are the methods by which a mind can be brought to that kind of expertise? The third piece, which hasn't come up very much today, except the conversation I had with one of our colleagues in the corner there, assessment, right? If we don't have good probes for either mastery or motivation, it's actually going to be very hard to improve what we're doing. So we actually have to have good measures of what's happening. And then tying this all together, we need platforms and a will to innovate and iterate rapidly, right? So this is all part of how you get iterative engineering to actually work for learning. Okay, so let's talk at least briefly about what I think is one of the more mysterious parts of this, which is cognitive task analysis. How do you unpack real expertise? Often people get panels of wise men and women together and ask them, what do you do? You're an expert nurse, you're an expert physician, what do you do? In fact, the research on expertise is a little depressing about this. So if you think about a top performer, somebody who by data is absolutely, a winning performer, call that 100% expertise. When you ask them, or when they are talking or giving a lecture or writing a textbook, you can demonstrate they literally will teach less than 30% of what a novice needs to know to be able to decide and do things in an expert way. I mean, we've all had the classic experience like the Nobel Prize-winning physicist who cannot explain first-year physics. It's partly because it's all in long-term memory. They have no words for it. It's no longer even accessible. So when you ask them, how do you do what you do, they don't even touch that because, well, that's obvious. And the that's obvious part can be huge for experts. That's why it's hard to teach kids to ride a bicycle the first time, because trying to remember what do you do with your hands and your feet, you no longer think about it. It's actually quite difficult. So there's a technique called cognitive task analysis and some variants of this where you have very expert interviewing. You bring the experts in one by one and you talk to them in great detail, and you can get another 50% of this. And it's based on finding those top experts, using data to find them, because opinions about who are experts often disagree with the data about who are experts. So you actually need to use data to find these folks. And then you interview them, you compare what they do, you create a kind of a gold standard of outcomes for this, and off you can go to actually do the training. When you do this kind of work, it turns out you can often shrink the instructional time by 25% or more, and you can increase the likelihood of reaching mastery by 25 or 30%. And there's been some good randomized controlled trial work on this in healthcare. There's been a lot of experience with this in the military and some other areas. But no one is actually doing this at scale in a systematic way. So it's one of the missing elements of our education development ecosystem, is a truly deep and systematic understanding of the outcomes. Now think what a problem that is, that we haven't actually done that part of the design problem, right? So we did this, some of this work inside Kaplan on an area that's, we train paralegals, people who help lawyers to do their work. And you know, when we compared our paralegal training program, which is very much like many other paralegal training programs, we discovered that only 4 of 13 critical paralegal tasks was even covered in our curriculum, which was based on standard textbooks for doing paralegal training. And so it was no wonder that the paralegal career path tended to be get your training, go to a law firm, have a terrible time, go to another law firm, have a slightly better time, go to a third law firm. If you're still acting as a paralegal, you finally are figuring it out, and now you can automate, and then you don't have to tell the next generation of students anything to help them. Well, this is the problem, right? That each generation of experts builds non-conscious expertise which they no longer are able to tell the next generation of students. So this caused us to realize that if we were going to do this properly, we'd really have to rethink the full range of outcomes that we were having students actually do. Okay, so let's quickly move to what does the evidence suggest about instructional design? So I have to delve a little bit more into the cognitive science world again. So the first thing is, when you look at how expertise develops, it goes through 2 or 3 well-understood or well-reviewed stages. You can recognize this even in yourself. The first stage, you could call a declarative stage. And you guys probably have had this feeling. You're trying to do something new, and you're working on a problem, and you realize, I just saw something relevant on the page before. It's not in my head anymore, but I literally just saw it, and I have to turn back. Okay, yeah, that's what it was. I know it was there. And you feel really stupid. What's happening is, everything has to go through working memory. You have nothing in long-term memory. And working memory is narrow. It doesn't hold very much, so it's easily flooded. So this is a difficult, slow stage. It needs a lot of motivation to get through. How can your instructional design help? It can help by giving you a lot of visual information so that you don't have to flip the page back. It's actually near you, it's by you, it's around you. Job aids, reference materials. Once you've done the tasks a few times, you start to have some of it put into long-term memory, and it now feels more familiar. It's not automated, you still have to think about it, but yeah, I know what the next step is. And now you're at what could be called a procedural stage. I can run this thing, and how do you help here? Here is when you can actually benefit from extensive coaching and feedback, because I got enough space in working memory to process it, right? In the first stage, I can't even hear anybody talking because I'm so confused. In this stage, you can actually process feedback. And then finally, for some aspects of expertise, not all aspects, for some, you can actually make it automated. You could make it just so natural, so quick that you don't even have to think about it. And how do you get there? You get there by repeated, frequent practice. You do it again and again and again, just like driving. You've done it so many times to drive home, you really don't have to think about it anymore. So, just to repeat, not everything becomes automated. So writing a convincing, persuasive essay, you're never going to be able to do that and think about lunch at the same time. It's a full-on mental thing you have to do. It uses working memory, but it relies on key skills that are automated as well. Okay? So this is the nature of how you actually build expertise. And so you've got to think about, well, what is the stage your students are at to then get the right instructional design to support them? Similarly, how many people here have heard of Bloom's taxonomy? Okay, so Bloom's taxonomy was developed before there was any cognitive science. So it's a fine logical structure, but it doesn't happen to be linked to what people know about learning and different kinds of outcomes and so forth. So Carnegie Mellon's Pittsburgh Science of Learning Institute actually has created a kind of a new taxonomy of outcomes that's an attempt to give the same guidance about what kinds of outcomes there are, but basing it on learning science. So the first step is the big chunks, cognitive procedures, like write a 3-paragraph summary of a 10-page article, right? That's a tricky, complicated thing, but you can get pretty good at doing that, and we really want students to be able to execute those kinds of complex cognitive procedures, if you will, okay? Backing that up, there are a lot of components. So there are facts, and fair enough, facts are facts. There are concepts, which are different than facts. Concepts are used by experts to classify situations. So in physics, is this a momentum problem or is this an energy problem? That's a really important first step for expert mechanics solvers in physics. They do that classification first. And you can classify without actually solving, and so the kind of practice you need for that is actually classification practice. And that really gives you a benefit when you do it that way. A third kind of component is when you have processes, complex multi-step pieces. Experts, again, they don't just know what those are. They can use them to diagnose a problem. If the output of a process is messed up, they know where it likely was messed up, and they can predict. If I double inputs in the process, they can predict what's going to come at the outside. And that's the kind of practice you need. And then finally, experts, one of the key things about experts is when everything else is foggy, when it's just confusing, they know what to do. Well, I don't know what's going on here, but the first thing we're going to look at is X. So they have some principles by which they can navigate very complex situations. And again, here too, the point is not to memorize a list of 5 principles. That's not what experts have. The point is to be able to use them, to actually have the experience of working your way through complex problems using those principles. And that's the kind of practice you need for this kind of thing. So, so all of what I just talked about there is cognitive stuff, the architecture of learning, the types of decisions you make, and so forth. Another piece we haven't talked that much about here today is motivation. So motivation is a key fuel. If you want people to do well at work or become fluent at things, there's real hard work involved. And the kind of hard work that the cognitive scientists think of when they think of motivation is that will you start, persist, and put in mental effort? Because if you will do those 3 things on a well-designed learning activity, you will change your brain because you're working it. You're running the neurons, right? Now, you'll notice liking does not appear there. Okay, that's one of those issues that people confuse liking and motivation. But for learning purposes, this is what gets learning to go. Now, liking is a reason to start, persist, and put in mental effort. But if you will do it for another reason, you will change your brain. Just like athletics, the weights, you don't have to love the weights to benefit from doing the weights, right? It's a matter of actually putting in the effort. So this is what cognitive scientists dig into when they're trying to figure out how to get students motivated. It's not liking, smile sheets are not helpful, it's this. And we had a very good cognitive scientist do a bit of a scan of the research literature on this, and what he found, there's basically 4 things that go wrong with motivation that you have to take apart. The first one is you don't value what you're doing or the way in which you're doing it. I'm a dancer in an algebra class. What am I doing here? And you stop. You think about dance, you don't persist, you don't put in mental effort, right? The cure, the treatment, somebody's got to explain to you why a dancer should care. Is it about the foundation you're going to run later on? And you got to have enough money to run it, and so you have to know about investment, and that means modeling, and suddenly you're in the world of algebra, right? So things along those lines. That's the first thing that goes wrong. Second thing that goes wrong, another dancer, same algebra class. I'm no good at math. Now that's totally different than the first answer, because now the problem is, I can't do it. So if the teacher or the parent talks to me about how important it is for your future, even in dance, you're making me miserable. My life is over because I can't do it. The reason I'm not starting, persisting, and putting in mental effort is because I can't do it. So the solution is completely different. The teacher or the parent has to be on the side of the student, problem solve, back up from where they're stuck, show them they can do math. Even animals can do math at the lowest level. I mean, you can do math. The question is, how do we get you to do this math? What's missing, and so forth. Totally different treatment than the first one. The third one is a little like the second one. You blame something in your environment. I hate this textbook. Who could learn from a guy like Bror? He talks too fast and waves his hands. You know, I can't learn from that guy. So you stop. It's not because you don't think you can do it. It's because I don't have enough time, or I can't understand this, right? Again, the treatment is totally different. It's about problem solving around that. Okay, if Bror talks too fast, take the tape and slow it down, right? There's ways to handle Bror talking too fast, okay? That can be done. The final one, which is the toughest, is negative moods. If you're angry, if you're frightened, if you're depressed, you're not going to start putting mental effort, persistent stuff, and that is as complicated as you imagine to solve. But it is different than the others as well. So motivation itself also has a research foundation, and this obviously gives suggestions for engineering solutions. Even the detailed work looking at individual screens, I apologize, this is an eye chart. The point of this is there's a lot of evidence about how to use media well and badly. For example, if you can take out irrelevant graphics, stories, videos, medias, and lengthy text, you can improve learning by more than a standard deviation in randomized controlled trial experiments, right? But you want to have graphics and text together. You want to actually have conversational audio in your learning environments for complicated topics. Those all help. So there is evidence to help. Now, what's interesting is people don't know anything about this. Richard Mayer, who here knows who Richard Mayer is in the cognitive science world? Okay, there's a few of you, that's good. Let me another experiment here. Who here knows who Jimi Hendrix is? So we're awake. Okay, the evidence shows we're awake. Okay, so who here knows that Jimi Hendrix is one of the world's most famous rock guitarists? Okay, I'm seeing nods at least. You haven't fallen asleep yet. Okay, great. So who here is a rock guitarist? I knew the reporter would be one, okay? So what we've proved conclusively is you do not have to be a rock guitarist to know one of the world's best rock guitarists, right? Richard Mayer, by data, is the world's most cited learning scientist. And in a room full of people who are interested in learning and success of students, almost none of you have ever heard of him. So that's pretty broken from an engineering perspective, right? That's pretty broken. But this is just, these are the kind of results that you can work with. And just for fun, because many of you may not, I have one of these up in my living room because I contemplate bell curves all day long. But for the few of you in the room who don't have this in your living room, bell curve, take somebody who's in the middle of it, move them by one standard deviation, which many of those interventions were doing, you've lifted them to the 84th percentile of performance. And that's by doing things like moving the text close to the picture or getting rid of the audio. That's irrelevant. Now, the research, that's science, right? And as always, your mileage will vary when you do stuff at scale in practice. But boy, it seems important to start from some of that kind of potential impact as we're thinking about what to do at scale from an engineering standpoint. So at Kaplan, we are trying to do this at scale. So for example, we took 9 different courses of all very different kinds. We analyzed them using a cognitive science checklist that we developed with the Gates Foundation. It's actually publicly accessible through the Department of Education, or you can email me and I can send it to you and so forth. And we analyzed our 9 courses. And dark here would be great. The lightest here is not so great. And some of these, you don't need, as from an engineering standpoint, to be all dark purple here. Personalization is expensive to do. So it's an okay engineering decision to say, I'm not doing that yet. But objectives? Not having good learning outcomes? I mean, I'm dying to have the debate with somebody who demands to have unclear learning outcomes. I mean, you can't even get to first base without that, right? And arguably, especially for Kaplan, because we've done a lot of work on test preparation, the assessment line is not so great. It means a number of our assessments are not very coherent or well-designed or valid and reliable, right? So we know, even inside Kaplan, and we're interested in this, we have a lot of work to do. A lot of work to do to apply these kinds of ideas and principles. And intuition is not the correct guide, okay? So we took a bunch of composition essays, and we compared the grade by the original teacher, so that's on the left, with marks by 2 other composition teachers who did not know the student, but who taught the same course. Those are the right 2. Now, Houston, we have a problem, right? Now, we don't actually know what the problem is. Most folks immediately assume, oh, the teachers are just helping their students out. That's what's wrong. But in fact, it could be the rubric used to grade essays is so badly designed that only teachers who know their students can give the right marks to students. Right? If you don't know the students, you got no hope because the rubric is terrible. So we don't actually know what's wrong. What we do know from this evidence is something is wrong with the assessments we're using. And I would argue most of our learning environments are not looking at our assessments in such a systematic way, and we need to. Because this is how it's been done for centuries. And it's not very coherent. Another example, we're very good at something called the law school admissions test, prepping students for that. There's a very hard part of that called the logical reasoning problems. And we're very good at this. So multimedia, tablets, we created an hour-long video plus a workbook. Fabulous, the Kaplan way for handling that. Then one of our learning engineers said, wait a minute, that's very complex problem solving, probably overloads working memory. We should try something called worked examples. Basically, have students look at worked out examples by experts. This is research from John Sweller. It's been going on for decades, and so forth and so on. And everybody laughed at him and said, that's ridiculous. We know video works. Everybody loves video. Video must be better. Okay, so we did a randomized controlled trial, 4 pieces, 4 parts of the trial. On the right is no preparation at all. Just to the left of it is what no test prep company in the world wants to see. An hour-long video in a workbook is a little worse than nothing. My colleagues tell me that's not a marketing campaign. Now, the good news is, statistically, the 2 right ones are the same. My colleagues tell me as good as nothing is still not a great marketing rallying cry, right? And this was surprising to everybody, that the video, hour-long video in a workbook, it literally didn't seem to move the needle at all. We did 15 worked out examples, and then we took 8 of them. We didn't know how many worked out examples to do. Both of those on the left are significantly higher than the 2 on the right. So it actually worked better for students. But here's what's really fun. Look at the time it took. The video and workbook was almost 100 minutes. 8 worked out examples was 8 minutes. So it took less than 1/10 of the time. It gave a better instructional outcome. And here's the final thing. That was 8 PowerPoint slides, right? This is an hour-long professionally produced video and a workbook. Cost of production, 20 times. But everyone was sure the video would be better. It caused the whole test prep organization to back up and realize, wait, we got to think about this differently. So your instincts, this should be an evidence-based thing. And if you don't follow the evidence when your instincts say otherwise, you're not doing evidence-based work. And we should do that. We should be doing this in our world. We changed a number of university courses that we had, virtual university courses, to take advantage of what learning science says about motivation, instructional design. We basically did the engineering thing of throwing the cognitive science kitchen sink at a set of 6 different university courses. And we were able to show significant improvements in the rate at which they retained, in their rate of passing the course, as well as their mastery of key ideas. So this was a big win for us, and actually caused our Kaplan University unit to actually start to engage in randomized controlled trials at scale. So Kaplan University has some courses that will have 1,000 students starting every month. Right? It's a virtual university, so they can start every month. So that means in January, if we're really doing this well, we could have 5 sets of 200 students in a randomized controlled trial experiment. We could do it in February, do it in March, and then start over in April, expanding and testing, right? This is the iterative development. So that in theory, by the end of the year, that one course, if we are working at speed, which we're not yet doing, we should be able to get 50 or 60 randomized controlled trials done. Now that's learning engineering, right? That allows us and others to actually understand more about what's actually going on. And so we've begun, they're doing dozens of randomized controlled trials in many different areas, motivation, worked examples, different things about media and so forth. And what's really interesting about, once you start doing more than one or two of these things, you realize you got to have a system. See, this is now engineering. This is process now. Because, you know, if you got 30 of these running at any time, they're at different stages. So we've had to build that as well. Others have not had that, yeah. So, but this is really the only way you can get this done. If you want to be systematic about learning engineering, about benefiting from the evidence that's already in place about learning, and then finally, benefiting from the generation of lots more evidence now. So thank you very much.
Excuse me.